Okay, well, first let me correct myself on this issue of flows. There are also line integrals, but with a twist, almost literally a twist, because the direction that matters is not parallel to the curve, but rather perpendicular. Okay, so the flow is going across the curve, and the mistake that I made was to say that there is a need to normalize that unit vector over here. So there does not have to be a unit, that vector n over there. It does not have, or should not, in fact, be a unit vector, which is kind of contradicts to what I said. But the thing is that what we are talking about, like I said, the perpendicular direction matters. Perpendicular direction of our flow, which is f, okay? And so how do we acquire it? So the one in green over there, right? So how do we do it? And the way to do things like that, flow or otherwise, is to take the projection of the vector f on the unit vector in the direction that we care about. Okay, so that part is okay, but then if we would do that, we would I overlook that the width of that base still matters. That edge we're crossing, that edge is not to be thrown out. The part of the curve is, in fact, the wider that piece is, the more flow crosses it, regardless of the direction. Okay, so which means that the length of that of t will still appear. And so when you multiply unit vector n by t, well, you have what you end up with. You end up with this. It is nothing but rotation 90 degrees in the counterclockwise direction. So that's how we do it. We look at the direction of the curve is going, and then rotate it 90 degrees. So I here rotated counterclockwise, but generally, the picture is counterclockwise. This is clockwise. That is counterclockwise. I turn it clockwise, but this one is actually clockwise. Anyway, so that wasn't right. So then the computation is that we're correct and the logic, more or less. You just don't normalize, so less work to worry about. And so we just rotate 90 degrees our direction of our curve, and the parameterization of the curve, which is p prime. Okay, and then you have your that vector you're going to need. This is the vector that you're going to need. So to be practically, this is the computation. So as you can see, we already had a unit vector already. This, when we reached p prime, it was already a unit vector. So when we took its 90 degrees angle, we did not have to worry about making it a unit vector, and so everything worked out just fine. So okay. So the lesson here is, let me make sure that I didn't make that mistake somewhere else. The major, I don't think so. The major lesson, I guess, is actually kind of something to worry about, is these two line integrals. They are side by side, and they seemingly have the same importance, and they're just only brings in more confusion than anything. So the flow integrals, line integral for flows, is so tangible that you really want to have it as some kind of a embodiment of a line integral. But on the other hand, it has this 90 degree turn that creates more trouble than it's worth. So if you want to go about understanding line integrals, maybe going to back to the original one work is better, because there are no extra issues. It is fully applicable to any dimensions, unlike the flow. And the only problem is that work is not as easy to understand. So if you're into physics, you probably you have some intuition about it. Otherwise, with flows, you can literally understand what it means. You can just put a bucket underneath and you can measure how much water flows across a particular front. Okay, so like I said, so if you want to do that, so maybe figuring out the line integral first and then looking for other applications would be a way to go. So I put an asterisk over there. So other applications, by the way, you can imagine how this problem of flow might be different. You can imagine that, for example, we are actually going through some kind of not just a front, imaginary front, but actually maybe some kind of an obstacle, and it might have a different degree of permeability. So maybe it's made of porous material, and it could be actually varying from place to place, maybe like this. So this one is porous and this one is less, and so easy to penetrate one part, the other, and you can solve the same problem with the same line integrals pretty much if you're willing. But it's better, probably a good idea just to learn what line integrals are before you get to more complex applications. Okay, so in fact, another one you can imagine probably there are some applications where the penetration is not only depends on the material but also direction. Have you heard of directional kind of materials? So maybe there are kind of pores in the material, but they are not going across; they're going like this. So you will be penetrating like in this direction, because of the nature of the material. So all of that can be done, and it is done modeling with line integrals. Okay, so that's the application of line integrals. But once to understand the mathematical concept, probably just stick with work, and the main thing is gravity, or if you're walking against the wind, and you think of the wind as it's like particles hitting you, and you feel it as a force. Okay, so then once again, you can understand the meaning of the line integral. Okay, so at the end we got to this point of circular or closed curves, and the typical situation of the work is in fact when the work is zero, and it is always the case, as we'll show shortly, is when the vector field is gradient, also known as conservative. Okay, but before we come back to that, let's just look at the general case of a line integral along a curve, which might not be closed necessarily. So I'm looking at integral of f dp, so work integral over c. Okay, so it's parameterized for making, so the formula is the same, but here's the assumption, a big time assumption that I make, is that the vector field is gradient. It is the gradient of a function f. Okay, and then what consequences are is we realize that we have what we have as the integrand is the result of the chain rule. Okay, so it is the gradient, the chain rule that was discussed not a long time ago, and that chain rule can be then applied backwards, and we end up with this. What do we end up with? So this is the right hand side of the chain rule. What's the left hand side? Well, I mean, if your the del symbol bothers you, just use the calculus 1 notation. What is this equal to by the chain rule calculus 1? F prime p prime of t times p prime of t is equal to
F prime. Big F prime.
And no, F, no, okay. How do we do it? It's the derivative of what? In words. If you don't know how to write it, how do you say it? What is it equal to? Derivative of?
It's derivative of the antiderivative of F
Well, no, not derivative of what?
Of F composed of P of T.
That's right. So it's a derivative of the composition. So F circle P of T prime, right? Or you can write it as like ddt of F of P of T. That's another way to put it. The same thing. Okay, so del is just the notation for derivative in dimension higher than 1. So I still, that's why I like this notation. Then you have only one formula to remember. Okay, so I'm using it. This is what I'm getting. Okay. What do I do next?
You just get F of P of T integrated or evaluated from A to B.
That's right. So what's the theorem?
It's the second half of the fundamental theorem.
That's right. Fundamental theorem calculus 2. Okay. So when differentiation and integration cancel each other, and I do have differentiation and integration, so it will be my function f of P of T. Evaluated from A to B, T from A to B, okay? And then familiar formula, it becomes then F of P of B minus F of P, I'm substituting of A. Okay, so we don't stop here, so apply chain rule, we apply the fundamental theorem of calculus from the usual fundamental theorem of calculus from calculus 1. There is one more step here, and that is the crucial part is what we have been talking about is this how much line integrals are independent of parameterization. So I could also make this parameterization parameterization free statement as simple as that f of b minus f of a, where, well, naturally a is equal to f of p of a lowercase, and b is equal to p of b lowercase, and these are the endpoints of our curve. Okay? That is called the fundamental theorem of vector fields. So, fundamental theorem of calculus of vector fields, I suppose. That way to put it. So we know, and it does come from the same, pretty much the same place. And okay, let me state it. So, fundamental theorem of calculus of vector fields. So suppose F is a gradient vector field. And suppose C is a curve, oriented curve from A to B. So both are in our end. Okay, and then the integral f dp over C. Okay, so line integral along curve C from A to B, oriented one, is equal to f of b minus f of a, where so once again C is from A to B. I already did that. I already wrote that, and the crucial part is then what is f? F is the potential function. So f del f is equal to f capital. Okay, so that's the whole thing. I could probably even put number 2 here, and I will, in fact. Number 2, emphasizing that this comes from the second part of the fundamental theorem of calculus, and also emphasizing that there might be a fundamental theorem of calculus vector fields, part 1. Okay, so this is part 2. As you can see, it is very restricted, very restricted, so always a good idea to check out the conditions before you jump to the punchline, but the key is that this is the key. This is especially dangerous if you overlook things such as continuity and differentiability. That is, we were used to that. This is even worse thing, because we know that there are vector fields that are not gradient. So some vector fields will not have this conclusion, the conclusion. So the theorem really totally fails under certain circumstances. For a vector field, just once again, the example would be of a vector field negative yx. Negative yx, the rotation vector field, it is it's not gradient vector field. It's not only it's not applicable, the result is not true. And the result is not true. It might not be obvious from this form of the theorem, but let's take it one step further, and we have a corollary. So under the condition of the theorem, this is what I'm going to assume: A is equal to B. Then we end up with a closed curve integral, like this, f dt. And what's the answer?
0.
0. Right. So f of b is equal to f of a. If b is the same point. So then for gradient vector fields, I'll put this. Once again, don't forget that this is a gradient vector field. So if the gradient vector field, then all circular motions will produce 0 work. Naturally, look at our rotation vector field. There is no way we're going to take a round trip, and then end up with nothing but with 0. The work will not cancel out. So you can walk against the wind, make a round trip, and walk all the way against the wind, and perform positive work or negative work at every time. Okay, so that's the key to the difference between dimension 1 and high dimensions. There's some things that are just not as obvious as in dimension 1, and this is the example that should be always kept in mind. Just like in calculus 1, remember, differentiable, continuous, not differentiable, or integral but not continuous, and stuff like that. So, derivative equal to 0, but it's not the maximum point. Those examples that should pop up in your mind right away as examples of limitations of the theorems that we have established. And this one is another example for calculus 3. So that rotation vector field line integral is not equal to 0. So W not equal to 0 for this round trip. Okay, so so that takes us to the next step, and that's what if we look closer at this theorem itself, what we discovered is that only the look at it, only how little matters. It's something that doesn't really come up in calculus 1 a lot, but look at it, the only function f matters, and even then it only matters whatever is happening in point A and point B. Okay, so so this is how we handle this. It's a definition, and so a vector field is called path independent. If vector field F, if such an integral depends only on the beginning and end points of the curve. Well, the picture is very revealing. So this is point A, this is point B, and I can take several curves, C1, C2, doesn't matter. The line integral will be the same. Okay, so once again you realize that the direction matters. you realize that that rotational vector field, once again, it's not gonna satisfy, because one thing about path-independent vector fields is that they all satisfy this property. Okay, so every path-independent vector field will have all its closed curve integrals, or closed contour curves, sometimes called contour integrals. It will be equal to 0. So once again, the rotation vector field we have here will not be path independent. Okay, so different trips will be different as far as work that the amount of work you're going to be spending. Okay, so actually, it probably makes sense to stop for a second and see what it means for dimension 1, because we are forgetting. I don't want to forget the connection to calculus 1 beyond just using it for theory. We just use the fundamental theorem for that, but really, what does it mean for these concepts become trivial? To begin with, this fundamental theorem of calculus of gradient vector fields is, in fact, once we go back and we just say, well, how about we set dimension n equal 1 here? What's going to happen? We will have the fundamental theorem of calculus from calculus 1, right? So there is nothing special about this integral. It is just will be the regular integral from a to b. Okay, so it will be integral from a to b. What is it? Fx dx. Okay. Right. Well, as you can see, the notation is slightly misleading in comparison to calculus 1, because we used f lowercase for the integrand, and the antiderivative was capital F. And we turned it upside down because, remember, if it is capital, it is a vector. If it is lowercase, it's a number. So that's, you can see that these are numbers subtracted here, but we're integrating a vector field. Okay, so it's capitalized. But other than that, f of x is equal to f of b minus f of a. So this is the quick version of calculus 1, fundamental theorem of calculus 1. It has exactly the same form. The question of independence of path it does not come up, because when you integrate from a to b, there is only one curve that we care about enough. It is that curve from a to b. Hypothetically, however, now we know we can try to integrate it like this, pass b and then come back, for example. What's going to happen? Well, that part will cancel each other, so it doesn't make any difference. So indeed, we have in dimension dimension 1, every vector field is path independent. Well, the vector field is just functions in dimension 1. Okay, so that's how we're going to be using it. In the meantime, so just let's not forget that. Let me state the less obvious theorem. The conclusion of the last theorem is every gradient vector field is path independent. The question that arises then, what about converse? So that's what we're going to be thinking about. So if you have a gradient vector field, then it is path independent, which is pretty much what fundamental theorem says, right? So it is independent of the curve itself. Only the beginning and the ending of the curve matter. Okay, so just like that picture indicates. But if we have a vector field which has this property, does it mean it is a gradient vector field? And the answer is yes, but it depends. Okay, so the converse is what we're talking about, and the answer depends on what? And the answer depends on the topology of the domain. So let me make a couple of topological definitions. And one is familiar, not related directly to this, but still worthwhile, so since we're talking about topology now. So a path connectedness. So a subset A, how about Q, of Rn is called path connected. I think I mentioned it, but very quickly. If for any A, B, and Q, there is a path, well, or there is a continuous permanent curve from A to B. Okay, so if this is my set Q, I have points A and B separated with each other like this, but then I should be able to find a path from A to B. Okay, so naturally if there's a break there, like this, okay, so the complication that you might encounter might look exactly like that, so you cannot tell whether it's a path connect or not, so that's a challenge, but so this is, if my point A here is here, B there, even though you can try to go directly, but then you're not allowed to leave the set. Okay, so so as you can see, you try to go from A or from B, you will hit the boundary of the set before you reach the other point. So this one is, and this one is path connected. It doesn't come up in Calculus 1 because the one-dimensional space is so simple, and the path connectedness is literally reduced to the to intervals. So path-connected sets are simply intervals. There is nothing else. Okay, so that it is really simple. Dimension 2 and higher, as you can see, these are the problems you face. Where does it come up? It comes up during for intermediate value theorem, for example. So on the continuous function, the image of a path-connected set is path-connected. That's a very variant of intermediate value. I'm sorry, no, intermediate value theorem, yes. Intermediate value theorem in higher dimensions, this is what happens, but only under the condition of continuity. So F is continuous. Okay, so this is just a mention that did come up a little bit somewhere, and it is crucial for a lot of things to make sure that our calculus works. So if your calculus, the domain of your function is broken into two, in other words, the path connected, the domain is not path connected, then you have all kind of trouble. So the two things are disconnected with each other, such as in the case of a function 1 of x. It has, the domain is made of two rays, so it has a gap in it, and then you have, as if you have two separate calculi, you're dealing with an entirely different way. So that's just more of a warning. It is a very common way of looking at things, and you probably won't make any mistakes there. But the next one is more crucial. Higher level topological feature is a hole. So we're progressing from cuts to holes. There is a subtle difference. So a cut. This is if I have a set and then I take a knot and cut it. Okay, so that makes it not path connected. Okay. However, I could also take a set and make a hole in it. So that's two very different topological features. And the latter one is what I want to talk about. It is more relevant to the topic of graded vector fields. So a hole. So what does it mean for? Or you can sometimes say if a tunnel is another good way to describe it. So you can imagine that there might be many holes, and the concept is not as simple as it seems, because imagine that you have a sponge. Imagine you have a sponge, and you ask yourself how many holes it has, or how many tunnels. Considering that those tunnels go all the way, and they merge and they split and they go in all directions, the question is highly non-trivial. Even the question, just to understand the meaning of the tunnel, would take some effort. So we are going informal here, and that, let me fix this. So just, it is a not really definition. So I put question mark. Okay, so Q is a subset of Rn. It's called simply connected. Don't ask why it's simply connected. It's not simpler. If every closed curve in Q can be contracted to a point. Okay, so if you say you have a square and you cut out a circle in the middle, you remove one point, just one point you remove, and then this kind of curve, closed curve, cannot be contracted to a point without leaving the set itself. So what's in blue is that this is my set, and it has a square with one point removed. Then as you start to contract your curve, it will not disappear into a point without passing through the missing point. Okay, so that's the idea of simple connectedness. So circle itself, as opposed to a disk, is not simply connected. So is simply connected, and this one is not, because it has one big hole. So you can take Rn, R2 minus the origin, not simply connected, once again. But if you take R3, now that's to think about, it is simply connected. So three-dimensional space, you remove a point, and it is simply connected, unlike the two-dimensional space. So that's the thing that happens with the as you progress with dimensions, things get more complicated, and there is some physical implications of this. Actually, the importance of the fact that the point does not just removing point from a plane is important, and if you remove it from three-dimensional space, is not so much. Okay, so and then this is the effect of having a hole in the domain. Is that whether we do or not, we can converse, or if it is a verb, to state the converse of our that theorem will be correct if, once again, the region is simply connected. Why it is the case? Let's see what the indication of why this is supposed to be the case is, once again, this example. I don't think I'm stating it correctly. I think I went in the wrong direction slightly. The problem with this one, the why this one is not. I'm not talking about the right thing actually. I'll get back to that. What I'm talking about here is the gradient test. The gradient test, and we had 3 examples of rotation vector fields in order in a row, and all of them were not gradient vector fields. But what was the difference between this one and the third one, which was this x over. So this is simply f. That's what I meant. G of x. G equal f over x squared. Remember this one? So it's the same vector field, so the same pattern of rotation is there, but we divide it by the magnitude squared, which makes its vectors are shorter and shorter as you move away from the origin, the exact opposite of what the original one has. So, which still makes it non-conservative, non-gradient, but the strange thing about it is that it passes the gradient test. Okay, so that is the inability, what I've been talking about, using their own words, is that the converse of the gradient test is what we're concerned with. Under what circumstances the gradient test has the converse, and the answer is when the domain is simply connected. Okay, so let me. Okay, so once again, example of f of x y equal to negative yx. So it's first of all not gradient. We showed that a while ago. And then it fails the gradient test. The gradient test, if you don't remember, it was py is equal to qx. On the other hand, if I take now my and take a new one, xy is equal to negative yx, and this time it is divided by x squared plus y squared. Once again, not gradient, but it passes the gradient test. Okay, so what's the difference between the two? Like I said, they have very similar circular pattern of motion, of arrows. Okay, the difference is the domain. Or domains. So R versus, R2 versus R2 minus a point. So from the plane we remove the point, and what does it do to two things? This one is simply connected, and the other one is not. Okay. Simply connected, not simply connected. So that's why the converse doesn't work. And the statement of the theorem is, let me state the theorem. Well, let me state the gradient test first. So gradient test. If f is del f, gradient, f is equal to pq, two components, then it satisfies this equation that I just wrote over there. Py is equal to qx. Speaking of naturally partial derivatives, so the x component is differentiated with respect to the y component, and the y component q is differentiated with respect to x. Okay, so one in one direction. Well, maybe I should make that clear. So this is the direction. F is the gradient. Then it is the equation satisfied. This is the converse. Okay, and I just stated here then the converse. It is a partial converse of the gradient test is if we still have to assume that f is differentiable. And secondly, the gradient test condition is satisfied. So py is equal to qx. Then f is gradient. Oh, and then I made a mistake that I promised not to make. I'll ask you not to make. What was the mistake?
We have to state that the domain is something.
Right. On the domain Q, which is simply connected. Then F is a gradient vector field. Okay, so crucial fact, the non-converse, we indicated what keeps us from stating the converse, and that is simple one little missing point in the domain. Okay, so that is, I guess there is a kind of a meta lesson here, is that the difference between dimension 1 and dimension 2 or higher is here. So if you sort of you only took calculus 1, then you might be, and you develop some kind of intuition for calculus, but then if you never get to calculus 3 and face something like that, that you might not actually understand properly our three-dimensional space. Okay, so that's the thing about it. So there are some complications that are not entirely predictable. I have been trying to state everything based on in calculus 3, based on calculus 1, and if you do everything properly, then things just grow. A lot of things grow directly from dimension 1. However, unless there is something really crucial that comes up as dimension increase. And that's an example when something really non-trivial happens that cannot possibly happen in dimension 1. Okay, so that's the converse. So then I guess we could do this side by side with what we did in calculus 1. You can't even say what it is, but if you take all the vector fields, then there are gradients, and then you can't even tell these are the gradients. Gradients are here, and then there is a lot of room. I want to emphasize that there is a lot of room for vector fields that are not gradient vector fields. If you think about it, the condition itself, just even if you forget about the non-simple connectedness condition or simple connectedness requirement, then still the condition of the gradient test is very, very restricted. So to one derivative equal to the other derivative, so we don't have a lot of freedom to begin with. And then we're also not allowed to, in addition to look at vector fields unless they are defined on a set that is has no holes in it. Okay. So as you can see, by the way, if your set Q is broken into 2, but there are no holes, then you're kind of in difficult position. But there is no trouble with having a gradient vector field. It is the fact that it is connected, but not connected in a weird way, that what creates the problem. It is it's like we remember ascending a staircase and then somehow ending up on the same floor. That's roughly what we're talking about. Okay, so once again, the examples are, I don't want to overemphasize it, but there are just so many examples of spaces that are not simply connected. The sphere also not simply connected. Is simply connected, but circle isn't, but sphere is, and so on. So in high dimensions, so the missing point is a problem in dimension 2 for sure. When you go to dimension 2, not necessarily. And why? Because you see you have so much room to get around it. And in dimension 2, you cannot. So if this was in dimension 3, I would just, if this is my circle, I remove a point, well, I can move my circle elsewhere and then contract it. Okay, so it's not so bad in higher dimensions. And once again, what I have suggested, that you have to look at high dimensions one at a time, and you don't know what you're gonna face. Okay, so dimension 3 is more complicated. Remember, there was by far there was a gradient test for the gradient test for dimension 3. Remember that one?
We compare the appropriate second order.
Second order mixed partial derivative. Well, they're not second order. They will be. Well, there are 3 derivatives each. And then if you talk about, a vector field has 3 components. Each of them have 3 derivatives. the three of those, well, so 9 derivatives. Three of those derivatives are kind of repeated derivatives. So x with respect to x, y with respect to y, and so you're left with 6, and you have then 3 pairs of derivatives, unlike 1 that you have to verify they're equal to each other, and that is the condition that I don't want to repeat. But you do form, what helps to deal with that is that remember those concepts of rotor and the curl. Okay, so for the rotor it's easy because it is just a function of 2 variables. For the curl that I don't want to repeat, it is a vector field, and the components are like this. So if I remember correctly, it's qx minus py times k. So remember the 3 components, and this is the 3rd component will be copied from a rotor. So the x and y are here, and this one is the z component of our space. So then once again the requirement then will be the requirement rotor of f is equal to 0, and in dimension 3 the curl of f is equal to 0, and that is the necessary condition for being right in vector field. Okay, so we'll just resume this.